right, it is Friday. Good to see you. We're trying to get your weekend off to a good start, even with a test looming there. That's a difficult task, but we will give it a shot here and hopefully help you out. Yeah, we are reviewing today. I think we covered all the material from Chapter 8. I think now the tough part is synthesizing everything, bringing it together, trying to see what factors trigger your thinking about one mechanism or another and what's the product here. So yeah, looking at reactivity now, it's kind of a different thing. We have to combine our thinking about structure and then guide ourselves through this idea of reactivity. What does this reagent do? Where is the part on the molecule that can interact with that reagent and produce this new product? That's the tricky thing, right? Homework 8, though, we said is due tonight, so get that homework uploaded. Test 2 is next Monday and Tuesday in the testing center, just over these 4 chapters, right? Chapters 5 through 8. And then chapter 9 will actually start on Monday. So yeah, alcohols coming up. Our next 3 chapters will be alcohols, alkenes, alkynes. We'll look at those structures in more detail, and they have sets of reactions for each of those functional groups. So you can kind of see now we're in the heart of organic chemistry, with functional groups being the main focus in their reactivity. All right, first let's do some reviewing here on the board. Then I've got some overhead stuff. Then I've got the sample test and questions off that. I've already been fielding some questions, people emailing me or office hours yesterday. So we can do that. I'll put up the sample test here on the overhead and field whatever questions you have. And I'll try to anticipate some of the questions that have arisen in previous semesters. So I think we'll go there. So here's the 4 reactions, right? SN2, SN1, E2, E1, and there are hallmarks for each one of those. Maybe we could review that. So for SN2, what? Primary, secondary, and what are we referring to there? The nature of the alkyl halide leaving group, right? And what type of thing here? Charged nucleophile. Okay, so include the charge there when you think about SN2. What about SN1? Well, it switches over here. Tertiary, secondary are better, and the nucleophile is neutral. Still has a lone pair, but it's neutral. So that should kind of trigger, your thinking about examining the structures, keeping track of their activity. E2, secondary, tertiary, and even primary. But here it's with a strong base. So yeah, switch it over to call that reagent a base now, because that's what the elimination is doing. It's grabbing a proton, right? And that happens faster from tertiary or secondary positions, but TB-toxide can even do it with primary. And then E1, tertiary, secondary, but let's say non-nucleophile, okay? Or very weak nucleophile. And remember, that's kind of a nuisance reaction. It's often mixed in with SN1. We don't want that result. If we want to do an elimination, we'll use TB-toxide and just get it over with, okay? It's done in minutes instead of hours or days with E1 with a non-nucleophilic thing. So that's kind of the rundown, I think, of just the basics to keep track of it. But let's do some reactions now. So sodium cyanide with this bromide. What type of reaction? And what's the product? You got to help me out here. Just shout it out if you see it right away. SN2, yep. And it'll be with the cyanide on there. Everybody okay with that product? Yep, thumbs up, okay. How about acetylene anion with this bromide? What type of reaction will that be now? I said it, right? It's the anion. The potassium here, don't be fooled by the metals, okay? This is plus here and minus on the acetylene. So what? It's a charged nucleophile, and it is small. That's another hallmark of these nucleophiles, small, okay? Because it's got to hit the back of that orbital, right? So what do you say here? What type of reaction for the second one? SN2 still, yep. And the acetylene goes on there. We make that bond right there, right? that product. Okay, what about sodium hydroxide? Again, that's small, but it is quite basic, but it is primary. So what do you say there? SN2, hopefully you said. Okay, yeah, that can still do SN2. And so these smaller alkoxides, hydroxide, methoxide, ethoxide with primary, will always do SN2. In fact, it's secondary. Most of the smaller alkoxides, even though they're on the basic side, will still do that. Yeah, you might see some E2 elimination mixed in there, but I think we're good to that point. And here is a secondary. Let's see, we've got a chloride here with a stereocenter. Let's see, what is that? I think that's S, right? So we need to worry about inversion of the stereochemistry, backside attack. So same thing with hydroxide here. Oh no, I just said it. That'll still be what? What type of reaction was that? SN2, okay. With inversion, this is now the R product, okay. And let's see, methoxide, same thing. Instead of the alcohol product, we'll have the inverted methyl ether product. Okay. Everybody still thumbs up to this point, agreeing. I won't make you vote on every one, but hopefully you can see them go by. Now here's a strange one, and some people were asking about this in recitation. Sodium iodide and acetone. Was this on the quiz too, quiz 5? I think so, yeah. And, you know, I said halides are bad nucleophiles. Why? Because they're not very basic. Nucleophilicity parallels basicity. And these are the worst bases there are, right? Halide anions are very happy, electronegative, they're happy as anions. But you can turn them into good nucleophiles or okay nucleophiles if you have something else going on. Here we're in acetone, which is a polar A product solvent. And that's able to solubilize, of course, the starting material and the sodium iodide to some extent. But acetone does not solubilize, does not bring into solution the byproduct, sodium chloride. So here's where you need to worry about the byproduct. Normally we just ignore the salt byproduct, okay? It's just washed away when we work it up. We distill these products. We don't worry about the salt in the end. But here we got sodium iodide, so that can actually do an SN2 inversion. And the key thing here is your byproduct, sodium chloride, is not soluble in acetone. Acetone is okay. It's kind of moderate polarity, right? It's just that little simple ketone. It's not like DMSO or water or those others that would easily solvate that. In fact, under those conditions, iodide wouldn't be a good nucleophile. But because this is insoluble in the acetone, it precipitates out as a solid that drives the equilibrium and allows this terrible nucleophile iodide to go on there, okay? So that's kind of a extra thing to remember. It's called the Finkelstein reaction. A German chemist identified that years ago, and it's become an easy way to make alkyl iodides, okay, using this selective precipitation. Anyway, file that one away. So over here, let's do a two-step thing. An alcohol, which on its own is what a weak nucleophile, it's neutral. That would be SN1 type nucleophile. But what are we doing? We're treating it first with sodium hydride. What's sodium hydride going to do to an alcohol? Yeah, it's going to deprotonate this. So think of that as hydride. This is plus. So we can take that pair of electrons on the hydride. That's H, right? Hydrogen with 2 electrons. We call it hydride, not a proton. Proton is the acidic form. This is the sodium, a salt of hydrogen anion, okay, or hydride. And so that can deprotonate here and form O minus, and the byproduct there is hydrogen gas. And as that escapes from the reaction, that's delta S being very positive, right? So that's going to make that reaction favorable. Plus the pKa of hydrogen itself is 38. So you see that's a very weak acid, which means hydride's a very strong base, okay? So it forms that first. Now we've got a good charged nucleophile, and now in the second step, we react it with the primary bromide. So what reaction do we expect to occur now? Which of the 4 is going to occur now? Come on, somebody yell it out, please. SN what? SN2 again, okay. Yeah, primary, there's our leaving group. And we're going to form the ether product, okay? So that's a way to form ethers from alcohols, which normally aren't very good nucleophiles on their own. But we can convert it first into this and then react it, okay? By the way, that's how we form these kind of things a lot. We'll say a lot more on alcohols coming up in chapter 9, of course, but that's combining the idea of the acid-base chemistry, the strong base here reacting with the weak acid first to form the alkoxide nucleophile, and then dumping that in the next reaction. So, okay, what about this one? Tertiary bromide with methanol. What type of reaction we're going to affect here? Think about it. If you got an idea, just yell it out. SN1, yeah. So why do you say that? Because it is tertiary. We can ionize via the carbocation. I was just talking to someone how they felt that the mechanisms were a unifying concept and really helping them out. And that should be true, okay? Look at the mechanisms as your friend, okay? But you should know how to draw the mechanisms for each one of these types of reactions. First, we ionize to the carbocation. That's step one. That's the slow step. But we're in a polar protic solvent, so that will help solvate both the bromide anion and the carbocation. And then eventually the nucleophile gets on there. We get to this point. We've got the hydronium ion of the methyl alcohol added to the carbocation. We got to get rid of that. And our final product is what? The tert-butyl methyl ether. Okay. Yeah. After we take off the proton from the intermediate. So it is a multi-step thing, right? But the first step, the slow step, is unimolecular, SN1, right? So that should help you unify that. All right, same thing here. We've got a neutral nucleophile. We've got secondary here with a stereocenter. What is that? S? Yep. So, yeah, and with this neutral nucleophile, it's not charged, so it can't do the direct backside bimolecular action. It's going to wait and ionize. And notice when that ionizes, what happens to your stereocenter? Your chirality, it goes away. Okay. Your intermediate carbocation is flat now, trigonal planar. So that stereocenter S is no more. Okay. So now your acetic acid can attack from the top or the bottom. And then what do you get? And I'll leave out the proton removal step. This is the acetate ester. And that stereocenter now is plus minus or R and S or DL. DL refers to dextrorotatory and levorotatory enantiomers both being there. You can't tell which is which. You could designate that however, but make sure you don't show clean inversion or retention of that stereocenter. It's been racemized now, right? Because it went through a planar achiral intermediate. The probability of attack now, mechanistically, can occur from either the top or the bottom. So your stereocenter went away. So there's some consequences to that, okay? Questions on these? Okay, let's put some more up here. Go through some more. And let's see. How about some elimination reactions? So here we go. TB toxide with a primary even. How about tertiary bromide with the neutral form of that tert-butyl alcohol? Might be a different outcome. How about this one? Primary chloride, water. And how about this one? Bromide up, methyl group back, methyl group up, hydrogen back with TB toxide. Let's see if we can do these. So we got TB toxide showing up, and that's your hallmark what? If it's the alkoxide, O- form, TB toxide, you're always thinking what reaction right away? Your default thinking should always be what? E2, yeah, okay. With all substrates, even primary, because it is so bulky and it's so basic, right? So what do we get here? Oh, we got a choice, so we can remove the proton on the right here. at the methyl or on the left at the methylene? What do you say? We're going to remove it. Which side? Who says the methylene side? Okay, there's a consensus there, I think. And yeah, we're going to form the more substitute alkene. That's Zaitsev's rule. And in this case, we have a choice between cis and trans. We should always form the trans one, being more stable than the cis. There might be a little bit of the cis, but don't do the elimination over here. Okay, that's the less substituted alkene. So you do have a choice sometimes. Here, it's not so much of a choice. There's only one type of beta hydrogen, and even with a primary TB toxide, we'll do the elimination. So what will we get there? Yeah, we will get the isomeric 1-butene product instead, okay? Because that's the only place. It's a bimolecular reaction. Happens all at once. You can do the mechanism here real quick. Do that. And remember, E2, we should always think about the hydrogen and the leaving group being anti-staggered to each other, 180 degrees to each other. And these acyclic ones can easily achieve that, okay? The cyclic ones are the ones we need to worry about sometimes. The stereochemistry can be an issue. But here's a switch in the reagent, right? Terbutyl alcohol. This is a neutral, hindered alcohol now with a tertiary bromide. So what type of reaction now? Is this still E2? No, it's not a strong base, not charged. So what do you think is going to result here? Go ahead. Which one? SN1 and probably what? E1. Yeah. So I'd say a mixture. In fact, I think at room temperature even, that is the major one because this is more hindered. But you've got this carbocation right here as the intermediate, and then the bulky alcohol that's neutral has to attack there or remove a hydrogen on the side here. But yeah, let's say either one of these could be a possible product, okay? Yeah, and there's, the mixture idea. I think I mentioned in class at higher temperatures, E1 can actually start to be more favored. Did I give you some a yield there? I think one went up to like 80% if we heated it up with a neutral nucleophile if it was tertiary. But this one at room temperature, I think, is the major one. All right, what about a primary halide with a neutral nucleophile? What's this reaction? Actually, it's not up there. We put 4 reactions up there. There's another outcome we didn't mention at the beginning, but what is it? No reaction, yeah. So here, a primary carbocation's not going to form, or it's going to be so slow, this reaction. You might be tempted to put some E1, the elimination thing here. But that actually takes days in order to occur. This does eventually decompose in water, but really you can take a primary halide or even secondary halides and stir them with water and they're indefinitely stable. Okay, nothing will happen. If you want to do a reaction here, if you want the alcohol, you would use sodium hydroxide, right? Just like we did before. That would be the way to do the alcohol because it would be done in minutes in DMSO, okay? But that's a different reaction. This is now what, SN2, not this non-reactive, no reaction SN1 with a primer, okay? Not a good combination. How about this one? TB toxide, yeah, we're back to our E2 champ here, right? And we've got a methyl here. We've got a tertiary bromide. We've got beta proton we can pull there. And we've got a beta proton over here. And notice that beta proton is trans to that leaving group. Now, why am I pointing that out? Because on a ring, that's what you need, okay? You need the leaving group and the proton that you're going to pull. They need to be across from each other, 180 degrees. Or what did we say on a ring here? Cyclohexane coaxial, right? They need to both be in the axial position. And you can get that from this. We'll draw the conformation here. So what would be the expected product here? And it is the Markovnik, or the Zaitsev product, right? This would be a tetrasubstituted alkene product. That's the major one. If we pulled this proton over here, you could do the elimination right there, but that would be a minor product, right? That would be a tri-substituted alkene. So hopefully you can see that this is the major one because it's the fully substituted, tetra-substituted. It has 4 sp3 hybridized carbons on this alkene, which is stabilized. What would the conformation of this thing look like? Well, we'd have to have the bromide in an up position. Yeah, so there's that methyl equatorial, the bromide axial, and let's see, yeah, there's this methyl, which is equatorial. Oh, and there's the hydrogen down in the back, sorry, is this one. It's axial also. You see they're trans to each other on the ring there. And so I think you can see the mechanism here is such that as these electrons are liberated here in the back, they fill right into the sigma star, which is right here, right? And that's your empty orbital that these electrons, each line means 2 electrons, right? Those electrons are flowing into that empty orbital to make the pi bond that engenders the 2 electrons in the pi bond right there. And we can look at this, you know, with the models a little more clearly. Here's our bromide, right? Here's our base. And if we grab that proton back there, these electrons can flow in and that can come off, okay? So the base, yeah, has to have a pair of electrons. That's the black line there in the ball here. And yeah, right there would be the one that's more stable because this group over here is a methyl also, okay? The minor one would be right here, okay? And that's a methylene carbon, the one in the front here. Is also down axial. But by Zaitsev's rule, we want to pull that one. Why? Because we've got a methyl back here, and that gives us the tetra substituted, okay? So that one's a little trickier. So for the cyclic ones, look for, you know, the hydrogen and the leaving group, both axial. Hydrogen and the leaving group. I think that's a corollary, I'd say, to that rule, that the better arrangement for the E2 being anti here, okay? On a ring, we're looking at those axial equatorial positions. Questions on that one? Yeah, there's a couple questions, I think, on the sample test that relate to that as well. Let's see, were there any others we wanted to do here on my chart? Yeah, I've got a couple more. Okay. Yeah, we can still do a couple here. Yeah, we will get to the overheads in a second. I think just doing enough problems is, you know, the better practice here, better use of our time. So here's another secondary chiral bromide. And then we've got, oh, that's kind of a complex looking reagent. Let's see. Oh, it's that thioacetate reagent. Okay. And then let's do TP toxide again. And let's do methanol. And how about this one? Yeah, here we got this. How about methanol again? And how about azide? Sodium azide. Yep. Okay. How about those reactions? So the thioacetate is a charged reagent. It's a relatively weak base. It's in that 5 to 15 pK range. Carboxylic acids are pK of 5. They're on the low end of that, so they're non-basic, similar to this. Sulfur is a very good nucleophile. It's a bigger atom, more polarizable than oxygen. And so our backside displacement there will give us the thioacetate ester product, okay? And we could throw some new nucleophiles at you. If they're new or the pK is unclear, we'll either give you the pK or show you the full structure and let you think about that, okay? But generally the smaller non-basic charged nucleophiles are what? Your typical SM2 nucleophiles. But that's not the case here with TB toxide, right? So there we're gonna go to the Zaitsev trans alkene E2 product. What about methanol? Now you could say this is kind of a borderline thing. It's neutral now. We're going to go through the achiral carbocation ionization. This is what? SN1 reaction. And then methanol can either come on the top or from the bottom. And so we'll get what? We'll get a racemic mixture, okay? The stereocenter will go away, okay? So you should say DL there or just draw it undefined. Okay, don't draw it inverted or retained. That's not part of the mechanism there. Same thing here, methanol going on this guy. We'll get the isopropyl stereocenter is still there. The methanol can either come in from the top or the bottom. We don't get a mix of enantiomers now. This one would give us what? A mixture of diastereomers. Okay, one up, one down relative to that there. Okay, maybe we can draw those two, right? How about that one up and this one down? And again, that's a consequence of the mechanism and the structure of the starting material, right? The starting material has two stereocenters. Our reaction's only at this stereocenter. That's where the leaving group is. This one stays put. And so we end up with this scenario here where they're diastereomers, the result of the, what, SN1 reaction. But if we go back to a charged small nucleophile, then what? We'd get our isopropyl group still up there. Our bromide's up here. Our azide now, will that be up or down? Will be down, right? Because it inverts, does the backside attack. So it'll just give us that trans product only. So you should be able to see here we get a mixture of the cis and the trans products, which are diastereomers. Here we just get cleanly what? The trans product. Does that make sense? Any questions on that? You can draw this out and see how that might look, right? So let's maybe do that. Here we have our isopropyl. Here we have our bromide and our hydrogen there. Well, our nucleophile is small enough, you know, to get in here and hit the back of that orbital. And when it does that, it pushes this hydrogen up. And so that hydrogen now will be up right there. If you can't see that, make a model, and hopefully that's more clear. And also on ChemTube, there's a bunch of examples of these SN2 type reactions where the stereocenter is inverted. Okay, you can see that because of the backside attack. That's where the sigma star is. Okay, but this is small enough charged nucleophile in order to get in there. Maybe we could look at that with the models real quick. So yeah, that bromide is equatorial back there. But, you know, so here's where the isopropyl would be, where my hand is. So how does that bromide get in there? Well, it hits the back of that orbital right there. By doing that, you see it pushes that hydrogen up. And then, yeah, I need to have another model there to show that. But yeah, that's the back of that orbital with that as the leaving group. Okay. Hopefully that makes some sense. Come up and inspect these if you want afterwards. Okay, let's go to the overhead here, Jeshurun, and go through a couple things and then the sample test. So here's the chart, I think, that summarizes everything in your book, and that's fine. That's what we've been talking about here, these conditions and the typical types of, well, no, this breaks it out to the type of halide, you know, and then what a strong nucleophile, charged nucleophile will do, SN2, that's what we've been talking about. But if that's secondary, also SN2, okay? If it becomes more basic, then we have more E2, okay? So you can break it out there and go through those same conditions we talked about. Here's my chart, which is probably more extensive, maybe more confusing. It's in a decision format here, so you start with an alkyl halide. It's got to be sp3 hybridized, not sp2, not vinyl or aryl, no reaction there. We talked about why there. If it's a charged, weak base, strong nucleophile, yeah, like acetate, you know, SN2 is your dominant thing. SN1 will start to occur if it's tertiary, though, okay? And I think we showed that with acetate early on with tert-butyl bromide. If it's a strong base, weak nucleophile like TB toxide, there you are. Everything's E2. Okay. If it's a strong base, strong nucleophile like methoxide or ethoxide, again, that's the basic side there. But those are smaller, so they're pretty good nucleophiles, right? SN2 mainly with primary and secondary. Tertiary, though, will start to do E2. Okay, so you can draw some more reagents here, to help yourself keep track of it, and draw some examples for each one of these boxes. That's a good way to review, I think. If it's not a base or a nucleophile, okay, with water that's neutral, no reaction, primary, very slow SN1. For secondary, tertiary, yeah, you'll get SN1, but a lot of E1 starting to show up. And if it's not nucleophilic at all, like acetone or toluene or just a solvent, it'll be no reaction or eventually just decompose via the E1 pathway. Okay, so I think everything's on that chart. Now let me give you some real numbers. I'm kind of lacking on this. I try to give you some yields from time to time or some relative rates. Your book doesn't do a good job of that. I apologize. I've pulled some out over the years from the advanced book, and this gives you some real numbers here. So these are the relative rates following the kinetics of these reactions. Methyl, primary, secondary, tertiary, again with the Finkelstein reaction, lithium iodide and acetone. The byproduct here, lithium bromide, is not soluble in the acetone. So even though iodide's a terrible nucleophile, it can work under these conditions. And look, with a methyl leaving group, wow, that's super fast. So this is normalized to the slowest one that can be measured here, the secondary. That has a relative rate of 1. That's done in minutes. It's a very fast reaction, okay? But these are super fast, seconds, okay? These are done here, methyl bromide and the primary here. The tertiary one is just too slow, okay? Because this is a charged nucleophile, right? I minus. This backside attack here is just too slow. Okay. Look at the range of kinetics there. Very, very incredible. You can look at a range of different primary bromides here with the same reaction where you have more branching at the beta position. Again, this is SN2. These are all primary. But look at this. This is unbranched here, the ethyl. The propyl, you'd say, well, it's just a bigger group here. It's a little bit slower. But then if you have the isobutyl here with a branch point there, then it's much slower. And then if you have a tert-butyl there, it's much, much slower still. Okay, this one takes hours to go. This is a special type of primary leaving group called a neopentyl group, which is notoriously slow for SN2 reactions. You would think, well, this backside attack should be okay. But draw that backside attack. It's got to come in next to this group here. So it's slowing it down, even though it's primary. Anyway, solvent effects, we've talked about that. The products and the polar A products both speed up SN2 and SN1. But SN2 here is dramatically faster with the A products because these have the ability to solvate the cation and leave the anion part, the nucleophile, unsolvated and more reactive. So in methanol and water's a little bit faster, and you see it's more polar, the dielectric constant's higher. But these, even though the dielectric constants are lower compared to water, these are A products. So that selective cation solvation makes these much faster. So if you run the reaction in DMSO or acetonitrile or DMF here, you get 1,000 times faster than the typical polar solvent there. SN1, so here we got the neutral conditions, and this is very dramatic. This is the most dramatic one, I think, with the relative rates. This one's done in seconds. In fact, it's hard to even measure it and see the starting material. Once you put them together, it's pretty much all done. And that's because it is tertiary, right? The tertiary carbocation is stable in this case under the neutral conditions. Secondary is also pretty fast, but much, much slower than the tertiary. And then the primary, super slow, and then the methyl could barely measure this rate, okay? It allowed it to normalize the relative rates here for the kinetics. So I'm not showing the absolute rate constants. Those are actually measured with these careful kinetic experiments. I'm just showing you the relative comparison of those rates, the K the K values that we've seen in our rate expression. More solvent effects here. And these are the product solvents for SN1. These go much, much faster in the product solvents because the bromide and the carbocation are both stabilized by product solvents. You can draw those structures out. You see water is a super fast one, and that directly parallels the dielectric constant that's measured for the solvents. Okay, the more polar that solvent, the faster those rates. Temperature effects. This is a borderline idea, remember, between SN1 and E1. Here I show you the ethoxide. This is a strong base one with a tertiary. It's almost all E1 in this case, okay? That backside attack on tertiary is slow, so it will give the Zaitsev product here 99%. But if we do this at room temperature with the neutral solvent, just ethanol, we get mainly SN1. That's what we taught you before in chapter 7, right? And here's E1 at the higher temperature, and some numbers there for you. 80% for the E1 in this case. Okay, I think that's good there. Let's switch over to the sample test. If you don't have any questions on that, let's see. Do I have it? Yeah. Okay. Is that showing up okay? It's kind of small there. Sorry. Make sure you pull up this document on Learning Suite. I know a lot of you are already looking at it. I'll go through and kind of point out some things now. And if you've got questions here, yeah, ask me that. Or when you're watching the video, email me with questions. And of course, we have office hours and recitation next Tuesday. So if you're planning on taking it Tuesday, you'll still have time to come in and get help. But don't forget, we're also starting chapter 9, the new material, on Monday. So hopefully you'll have a little time to glance at that chapter. Sorry, it's just the nature of the chapters and how they fall there. We've got to start that new chapter while test 1 is still being offered. Okay, so let's look through this, see what you want to look at. So some definitions, what's a nucleophile? What's an enantiomer? Stereoisomers that are chiral and non-superimposable mirror images. And some other definitions there you should be fully aware of, right? Diastereomers, meso compounds, achiral compounds. That comes out of what? Chapter 5, going back to that. And now we're connecting those ideas, those concepts, with the reactivity. So that's the new thing, I think, in chapters 7 and 8 there. But plane polarized light, you should know something about, the optical rotation, whether it rotates to the left or to the right, and the percent optical purity, comparing the optical rotation of the pure enantiomer versus a racemic mixture, or some sort of a non-pure mixture there. We talked about the enantiomeric excess. We talked about Gibbs free energy and the different factors of that. Gibbs free energy is negative, that's exothermic, yeah, that kind of stuff. Here we are getting right into reactions, the types of reactions. Those were summarized also early on in chapter 6, I think. So here we're looking at substitutions and eliminations for these reactions, right? And let's see. Yeah, there's a racemic definition there, 50-50 mixture of enantiomers. Some naming, not a lot of naming, but know how to do the IUPAC naming there. And make sure you include the stereo centers as part of your name. If it's multiple choice, it'll be right in there. Make sure you check all of them to make sure you got the right numbering and the right RNS there. What's chiral, what's achiral? Let's look, the chiral compound. That's achiral, that's not a stereocenter. That's a meso compound, C, that's achiral. D is achiral, mirror plane right there, but there's no mirror plane here, right? So I think that's the SS enantiomer there, where they're trans and to each other. But yeah, that one's a little bit tricky there. Hammond postulate. So this comes up sometime, and we can talk about this specifically. We've only mentioned the one where if it's a endothermic step going up to an unstable carbocation, say with an SN1 type of reaction, That transition state then reflects the character of the carbocation intermediate because that's closer in position to it. If it's an exothermic step here, look, the transition state is closer in nature to the starting material, okay? So that's just the opposite of how we mentioned it in class. The book discusses these two scenarios, though. If it's an endothermic step, you know, the energy here, the intermediate, would be much higher. And there, the transition state's closer, and more of that nature of the carbocation is borne out in the transition state. So that's what it's, Hammond's postulate says, things that are close together on their reaction profile reflect each other, okay, have similar character. That's all it means. But you can state it different ways, and hopefully that'll be okay. We can draw little transition states of the different reactions. So this one, as it's drawn here, is just ionizing to go to the carbocation. And I'm reminding you that's a slow step. And so what? That's the rate determining step for SN1. Okay. Yeah, it could be the same for E1, but that's not one of the choices there, right? But you can rule out the other ones there. Rate expressions, know what the basic expressions there are for E2. Bimolecular ones, you need the two things there. So that would be similar for SN2 also. Okay. And faster rates, I just showed you some of the numbers on things like that. Zaitsev's rule, yeah. DBU, that position of protonation is, yeah, see. Oh, this one here, 19. Somebody said, well, you didn't have us memorize all these pKa's. How do we know which is the strongest base? Okay, well, look at, you know, I'm trying to force you to think about the structures, okay? And what if you have a negative charge on oxygen, that's electronegative, right? And here, negative charge on oxygen. And look, negative charge on fluoride. And that's the most electronegative atom. So that's what going to be the weakest base, choice-wise here, right? And now we have a negative charge on a less electronegative atom, the nitrogen. Yeah, that's going to make that a much stronger base. In fact, the pK of ammonia is what, 38? So that's very strong. Comes from a very weak acid, right, ammonia? Whereas this came from water, pK of 15. If you want to know the pK values, memorize them fine. pK of carboxylic acid, that one you should know, 5, right? So you got 5, 15, 38, and 3. So which one's the strongest base? This one here, from the highest conjugate acid value. But you can look at it from electronegativity and which one's happier with the negative charge. This one's not as happy with that negative charge, so it's going to function as a stronger base. That's what I'd like to get you to think about instead of just memorizing a bunch of numbers. Same thing here. If you protonate there, you get a resonance structure. And then we got, you know, and this will be typical of our test too coming up. There'll be some sort of chart with a bunch of product choices, right? You should be able to inspect whether it's primary, secondary, tertiary, just like we've been doing, and then pick the correct product here based on what type of nucleophile is, charged or neutral, okay? And then the stereochemical outcome. And then some labels here to keep track of some things. DL, there's the one where it's racemizing. Yeah, and we mentioned one there. Here's one where it's cleanly inverting, so you should list the two stereocenters. Yeah, so I think we've been discussing stuff like that. And then analyzing, you know, compounds with multiple stereocenters. Here there is symmetry, so there's a possibility of meso. It's this one here. That's the same compound right there. These are the same. And then the RR and the SS are the two enantiomers, the two chiral ones. Similar analysis here, but these are all chiral because chloride and bromide are not symmetric, right? So here you had two chlorides, so there you had the symmetry in there. So that goes back to chapter 5. And here's our first one with a chair, looking at the diaxial arrangement there. You're told something different about the kinetics here. Oh, no, you're told one gives substitution, one gives elimination quickly. And so it's this one here that has the bromide locked axial, which will do the elimination quickly. With what base? Oh, methoxide, okay. So that's a strong base, right? And if it's locked in this axial arrangement, because the tert-butyl group has to be equatorial, right? So if there's cis there, so drawing a picture, a good picture is worth 1,000 words here. If you're asked something, details about the mechanism of stereochemistry, make sure you draw a good picture there. You can take your models in the testing center, have cyclohexane all ready to go. There'll probably be one like this on the test. So we want to see your ability to analyze and compare possible reactivity based on stereochemistry. That's higher level thinking, I think. It's synthesizing the material, thinking about the reactivity and the structure and the stereochemistry. So it's multiple concepts to master there. But you can see this one's in the equatorial position. It's not optimal for E2. And this is a small enough nucleophile methoxide to hit the back of that orbital and give you the cis product as the SN2 pathway. Okay. This one's exclusively E2, you're told. And this one here gives mainly SN2. Anyway, yeah. Questions on that one? That should be okay. Here is kind of a caveat or an exception to the rule, you could say. Some things that, even though they're primary, can still be relatively stable carbocations if there's some resonance stabilization or something else donating or helping the carbocation form. In this case, if you have an oxygen nearby, you've got resonance stabilization there. So you were told one of these was very fast, and this one gave no reaction with water. And so you had to analyze this and point out this one had resonance stabilization. Okay. And again, draw some nice pictures, the rest of the mechanism, and that'll help you get full credit there. This is probably the toughest one on this exam. We did give this on an actual exam. This is a very hard problem, I'd say. Don't worry, not all the problems on our exam will be of this level, but there could be, you know, one or two that's harder this way. You're given the products here, and so you just have to come up with a pathway that leads to those products. So it's a mechanism that we haven't covered that you can think about this. Hydroxide can deprotonate a thiol. The thiol pK is actually 10. So that's favorable to form S minus here. And then you're forming a ring here, and why not add to this alkene? That's where you need to form that bond right there. And then you form an anion next door to the cyanide. Now the cyanide by resonance can stabilize that anion. So it's an intermediate anion there. And then that functions as what? An charged nucleophile to open up the epoxide. Okay, so that's like an SN2 reaction. It does invert that stereocenter there. And you get the two different products, whether the thiol adds on the top of the alkene or from the bottom. Okay, so this requires a little more analysis. Use your scratch paper with these type of products. Experiment with it, try different things, and make sure what you're coming up with, you know, answers the question fully. Here you had to come up with a mechanism that could account for both of these two products, A and B. But pushing electrons makes sense if you get started right using acid-base ideas. And then what nucleophiles? A thiol nucleophile, and then the cyanide nucleophile to open up the epoxide. Okay. So experiment with it, try a couple things, and apply the principles the best you can to a harder problem like that. Again, we're not giving you a ton of problems like that. I hope they don't all appear like that. Okay, but struggle through that one. Try it on your own, see if you can reproduce it, and that kind of gives you an idea of how you can bring together multiple ideas here. Same thing here with this one. What do we have? This is just drawing out the two mechanistic pathways leading to the SN1 product and the E1 product here. So yeah, the carbocation's the key thing there, and then the attack, and then loss of the proton there. So I'd view that as an easier one. Those are the standard mechanisms we expect you to know, okay? And there might be ones like that. This one here is a little bit trickier because it's got this norbornene skeleton, this bicyclic bridge thing here with the tertiary bromide at the bridgehead position. Now that's locked to be kind of in a pseudo-equatorial position. It's not anti to any of the beta hydrogens. So that's why this one is so slow, okay? This one reacts fast because, you know, you got 9 hydrogens that can all get anti to that bromide. This is okay for the elimination. And also here, the elimination, if you do eliminate here, look, that puts the alkene at a bridgehead position. If you make a model of that, it can't get flat. You can't get the alkene overlap there. So this is actually a very slow E2 elimination. Eventually it will eliminate. It'll actually rearrange to give a different type of product here. But the sigma star, I would say, is unavailable. It's in the interior of this polycyclic structure, whereas this one's readily available, the sigma star. Okay, so there's an analysis based on the stereochemistry. But yeah, it's kind of implied one will react faster than the other, and you explain why. Okay, the one does. I think we're about out of time. The worksheets are also here. These are harder problems. These numerical problems, I'm not putting those on our test. I like to show you how some of these can be solved, though. Don't worry about that. Especially this one, the delta G thing with the log K expression. We're not having any numerical things like that. But certainly all these structural ones and the conceptual ideas are a little bit harder here on some of these worksheets. You can work those and ask us about those, and we can help you out. So very good. Hopefully this review was useful for you today. But contact us if you have further questions, and we've got some things coming up. So good luck on the test. We'll see you next Monday. Have a good weekend. Thank you.